Hi, and welcome to Introduction to CAESAR-Lisflood. So to start with, CAESAR-Lisflood was designed to model landscape evolution, or how geomorphic processes, notably fluvial processes, alter the surface of the land. And so first we're going to just talk a bit briefly about some of the principles or some of the background that affects that. And what better place to start with a map of the South Island of New Zealand, where we have these lovely mountains of the Southern Alps draining across these big braid plains or floodplains that are made up of all the sediment that is eroded from these mountains and being deposited as it goes out towards the sea. You can even see the sediment plumes where it's reaching the sea there. And it's much the same principle as we see within this basin, which is the Amazon basin, or one of the largest rivers in the world. We have material from the left-hand side of the image, the Andes Mountains, running along the left-hand spine of South America, uplifting at rapid rates, the driving erosion because of the gradients that then transports the sediment down across through the Amazon basin and out to the sea. And so rivers have been described as being therefore vital in controlling this process of how sediment moves from the mountains to the bottom. And they have been described as what we call the jerky conveyor belt. Okay, as in it's a conveyor belt for this sediment from the mountains down to the sea. But it's jerky because it's not continuous. It's operating every now and then. When there's a big flood event, or when there's a big input of sediment from a landslide or something, for example, then that speeds up the conveyor belt. And ultimately, how this conveyor belt operates shapes the landscape, not just at the bottom, but it also shapes how rapidly material is removed from the mountains, and that in turn shapes how rapidly the mountains uplift, and even shapes the shape of the valleys and the mountains in the upper ranges. So, for example, and this is some work, seminal work by Alan Howard in his drainage basin evolution model, early landscape evolution model. So here we have a landscape where the conveyor belt is always running. It's a badland landscape. Okay, so we have hills that are very easy to erode, and every time there's a rainfall event, material is eroded and it's moved downstream. And we get these quite straight hill slopes and a very high drainage density or high drainage network. So the same model, but here we introduce a jerky conveyor belt. Okay, so the conveyor belt can only move when an erosional threshold is passed. So you can only have material transported when there's a certain power to the water to move it. And this actually gives us a very different landscape shape with far more convex hilltops and slightly concave valley bottoms, as we can see here on the left. And when we look at a map of what this looks like, we can see we have a much smaller drainage network, again with these concave hilltops and convex bottoms. Now, we can throw into the mix of this the relationship between vegetation and how that affects erosion and deposition. And again, some classic work by Langbein and Schum back in the late 1970s looking at reservoir data and reservoir sedimentation data. And what they found out was that when you have very little rainfall, as we have on the bottom left-hand side of this graph here, you have very little sediment going into reservoirs or going down rivers because there's no water to move the sediment. Then as you get to precipitation rates of around about 400 millimetres a year, so a semi-arid environment, okay, there's not enough water to support a dense vegetation cover, but there is enough water to move a lot of sediment. Okay? So you start to get very high sediment yields. Okay? But then as the amount of precipitation increases, then more vegetation can grow, and that locks in the sediments in the top, reducing erosion, and the amount of sediment coming out of rivers and sedimenting out in reservoirs decreases. So we get this lovely curve, the Langbein-Schum curve. So when we're trying to model landscape evolution in models like CAESAR-Lisflood, we have all sorts of difficulties just because of the sheer number of processes that are involved. I've just sort of sketched out many of them, but not all of them. We've got fluvial processes, erosion, deposition, and within there we've got gullies, terraces, canyons, floodplains, alluvial fans. Then we've got slope processes like landslides, rock landslides, soil creep, rain splash, rill wash, gelifluction, the generation of soil itself, pedogenesis, weathering of bedrock. And then we have even bigger processes like tectonics, uplift, rebound, unloading, isostasy. We also have glacial processes, vegetation process that we just talked about, and of course us humans, what effect that makes. And so this is one of our problems when modelling landscape evolution. We have many processes acting at many scales. This is a classic diagram. We've got time on the y-axis and space on the x, and we can pop in some of these processes here. So plate tectonics takes a long time and operates over huge areas. Then we have turbulence in rivers, very short time scale, very small space scale. We've got landslides. They happen quickly, often, but they affect a large area. Then we have things like river braiding that sit in the middle. Soil creep takes a long time but occurs in large areas. Sediment transport, river meandering. And over the top of all of this, we have how do things such as vegetation affect this? How does human action affect all this? And of course, how will changing climate affect all of these processes and how rapidly they affect? So these are just some of the challenges we have in modelling landscape evolution. And tied into that is a problem of our short observation record. We only have records, instrumented records of geomorphic processes going back 50, maybe 100 years. And what that means is we don't have a full picture of what's going on here. And here's a great cartoon by Gary Larson, The Far Side. So we've got some cows standing up in the field. One of them shouts, "Car," and they all sit down or go on all fours and pretend to be cows when the people drive by. And then when the cars pass, they all stand up again. And the cars driving past is us. We only have a short window or very short glimpse of what's happening. And we don't know if all these processes we're modelling or think we have a good understanding of operate in that way over much longer timescales. That is one of our key assumptions. So linked into this is what we call the Holy Trinity, and controlling many of these landscape evolution processes are what happens within rivers, and predominantly the feedbacks that operate within rivers. Okay, because we have the flow, the turbulent flow up on the top left here. Okay, then that flow of the water drives sediment transport that we see on the right-hand side here. We've got some nice bed of a river. Okay, then the movement of that sediment, okay, then can change the pattern of the river, like this braided stream we see at the bottom. Okay, but then the changing pattern of the river, or the shape of the river, the morphology of the river, then changes the flow, which then changes the sediment transport, then changes the shape, then changes the flow, and so on and so on and so on. So this is called the Holy Trinity of fluvial geomorphology, if you like. But it's this positive feedback, okay, between all these mechanisms that basically makes rivers so complicated to predict. So why did we develop CAESAR-Lisflood? Well, this happened 25 years ago. Well, back then and still today, we found there's a bit of a dichotomy or a split between two different camps of models. On the one side, you had very high resolution computational fluid dynamics models that could model water flow and sediment transport fairly well, okay, but they were complex. They required lots of computing power, and they still do. And because of this, they often were limited in the spatial areas they could model, because you can only run, because of the model complexity, you can only model with a certain number of grid cells, for example. That limits the area you can simulate. But it also limits the time you can simulate. So you may only be able to simulate a reach of a river, like we see on the right-hand side here, this lovely braided river simulation. But you can only simulate it for maybe an event or a year or a few months. Yet on the other side, we have these models we can see at the bottom here, very coarse resolution landscape evolution models that used coarse grids or meshes to represent the landscape, and water was very simply routed down them, and you moved material from one grid cell to the next to represent sediment transport. So these operated over geological timescales, if you like, and had sediment transport. And the fluvial processes were very coarsely represented in very large grid cells. And so this led to what we call a modelling gap, which we hope to plug with CAESAR-Lisflood, where we have timescales of 1 to 100 to 1,000 years, timescales that are important to practitioners, people looking for practical issues in drainage basins, our length accurate records, and also our human timescales, if you like. Something that could operate over a sensible or a reasonable grid resolution, say 5 to 10 metre grid cells, because there's no need for very fine grid cells for most problems. But we needed to have morphological change, to have erosion and deposition represented, and represented reasonably well, because it's an important process in the development of catchments. A need to incorporate the catchment, not just look at a reach to try and simulate the whole catchment, and to account for the history, the stream behaviour, both upstream and downstream. And really wanted 2D or greater for the representation of this, because erosion and deposition is a 2 or 3D problem. It'd be great to have the stratigraphy built up over time. And so, yes, this led us to develop CAESAR and then CAESAR-Lisflood, which is a 2-dimensional flow and sediment transport model. So it can model multiple grain sizes, suspended sediment, bed load, erosion, deposition. And it's designed to simulate morphological changes in river catchments. And this is an old slide because it's been applied to over 100 different catchments and reaches. There are over 100 papers where people have used CAESAR-Lisflood in a wide variety of different places. And a key difference from these longer term landscape evolution models is that CAESAR-Lisflood models can model every single flood event. So it models a sequence of time on a flood by flood basis from years or a single event up to several thousands of years. And that's an important difference rather than using an average of events or a representative event. So it has 2 modes. We can run in reach mode or in catchment mode. And this allows you to run over a range of different scales. And you can actually have to run a catchment mode model, let's say a coarse scale model of the catchment, and take the output from that and feed it into a finer resolution model of a reach. And an old slide from one of the first papers on CAESAR-Lisflood, but it describes its structure. We have a river catchment. Our landscape is represented by grid cells. Then each cell has properties for the elevation, the depth, flow depth, discharge, the vegetation cover, and the different grain size components of that cell, the different grain size fractions. And then for each time step, this cell is changed according to laws which fall roughly into 4 groups. So we have a hydrological model which works out where water goes in the catchment from an individual rain event. So you just input rainfall data and it tells you where water is going to go. A hydraulic routing model which then routes that water when it comes in. Then once you have the water routed over the surface in the rivers and river channels, you have depths and velocities, and you can then use that to drive fluvial erosion and deposition rules. And then finally you have slope processes such as mass movement and creep that can act to introduce material into the channel. So the hydraulics are now based on the Lisflood FP formulation, which follows this set of equations here, has a representation, basic representation of momentum using flow from the previous iteration. The easiest way to describe this is a bit like, it's not a full-blown 2D solution to the Navier-Stokes equations. It uses a sort of empirical approach. It kind of works Manning's equation in 2 directions at the same time. It's probably the best way of describing it. Okay. And this gives us flows in our 4 Cartesian coordinates, north, south, east, west, if you like, between individual grid cells. And the time step is contingent upon a Courant condition, which is loosely dependent upon the flow depth and the velocity, the movement between cells. And this is important to stop numerical instability happening within the flow equation. And it works pretty well. Here's an example from some benchmarking study where we have a dam break or a massive release, which is this hydrograph on the bottom here of an inflow of 3,000 QMX, 3,000 meters cubed. And each one of these red dots, 1, 2, 3, 4, 5, 6, represents a gauging station down this valley. And we can look at the comparison between the gauged outputs at these, or we can look at the comparison, between regular Lisflood outputs at these points and the CAESAR-Lisflood outputs with our black and our coloured lines here. So we see a good comparison there. And this study is, these results are actually part of a larger benchmarking study that was published in the UK, carried out by the Environment Agency to look at differences between numerical models. Here's an example where it's been used to map inundation modelling in Carlisle, when we have a known flood event, and the yellow dots are where we have surveyed trash lines, the extents of where the flood water had gone, and here we can see the model outputs running through the middle here. And one of the advantages of CAESAR-Lisflood, or Lisflood FP of Lisflood as a routing algorithm, is it's really quick. So this model of Carlisle that we have here will run a major flood event through it in a matter of 1 or 2 minutes, if not less, on a good computer. And it's this speed that allows us to use this flow model when we want to simulate tens, hundreds, or even thousands of years. So for erosion and deposition, it's fluvial erosion and deposition is characterised by the interaction of different grain sizes in both bed load and suspended sediment transport. And here on the right we have a great example of this. This is the same bit of riverbed, and the top is the normal riverbed, and when we scrape it away underneath we can see much finer material. So we have an armouring effect here. Fine material is winnowed away to leave a sort of protective layer on the surface, if you like. And this memory effect, because that coarser layer in the top picture is now harder to erode than the layer underneath. So it's important to capture effects like this. And if coarse material then gets buried by finer material, it may then create a harder layer to erode in the future if the river should incise down to it. So this interaction of multiple grain sizes and the memory effect is really important to capture within the model. And so we managed to do that within CAESAR-Lisflood by using a series of active layers to represent the different grain sizes at different depths. So here's an area of floodplain in Wales in the UK, and here we have some water flowing across it showing inundation. And these are the patterns of erosion and deposition that we have after the model's been running for a while. So we have erosion in the channel, we have deposition on the floodplain, and we get really nice features here as well, such as levees forming next to the channel, where you have material preferentially deposited close to or next to the channel. And then if we look at the grain sizes across these cross sections, we can see that we have the deposition of fine material in the levees and coarse material in the channels. So the model is really nicely replicating some of the effects we see within river channels with preferential erosion and deposition. And we can also model lateral erosion. So here we have a meander in the River Severn, and we can digitise this from maps back in 1857, and we can run a simulation. We move through time, and we can get the model to do some quite nice results that simulate what seems to happen in nature quite well. Here's another example where we have lateral erosion in another bit of the River Severn in Wales, in CAESAR, and it's not double vision. It's where I've sort of got opacity or transparency within two aerial photographs and drape them over each other. So we have two different pictures of where the river is, and we can model with CAESAR-Lisflood where the river changes to really nicely up to a point, and then after a few years things start to not work so well. And that's because like climate models or models of the weather forecast, for example, CAESAR-Lisflood tends to predict quite well in the near future the morphological change. Once you get beyond that, giving you exact patterns of erosion and deposition become more difficult. So you can add water as rainfall, or you can add water and sediment at specified locations if you want to run CAESAR-Lisflood in reach mode. You can have an input discharge file, which where you can input the water in, and we'll go through these in a tutorial hopefully. And these are the different lines in this input discharge file. We have the time, the discharge, then we have the sediment, and we have all the different grain sizes of sediment that's input. We can also run CAESAR-Lisflood in both catchment and reach mode, so we can generate sediment in the top part of the catchment at a coarse resolution, producing hourly water sediment data, then use this as an input into a reach mode for a more detailed section of the lower part of the catchment, if you like. And when running in reach mode, we can also recirculate sediment. So if we don't have input data of water and sediment, we can take sediment from the outlet and feed it back in at the inlet, and we can feed in 100% of the sediment, or it can be a percentage of it.